I'll be doing problem 4.2 in Griffith's Introduction to Electrodynamics. So according to quantum mechanics, the electron cloud for a hydrogen atom in the ground state has a charge density rho of r equals q over pi a cubed e to the power of negative 2r over a, where q is the charge of the electron and a is the Bohr radius. Find the atomic polarizability of such an atom. So in this picture, I have an atom where this is the electron cloud, and the center of the electron cloud is here, and here's the nucleus, and it's displaced by some distance r. So when we look at the equation for dipole moments, it is defined as dipole moment equals alpha times the electric field, where alpha is the, in this case, where alpha is the atomic polarizability. This problem is similar to example 4.1, except we don't have a uniformly charged electron cloud. Now our electron cloud is dependent. This problem is similar to example 4.1, except this time we don't have a uniformly charged electron cloud. So we can start by looking for the electric field. And in this case, because rho of r is only dependent on r, there's symmetry, and we can use Gauss's law, where our Gaussian surface is a spherical shell of radius r, as shown in the picture. Gauss's law is the integral of E dot dA equals Q enclosed over epsilon naught. The electric field for this Gaussian surface is constant, so we can take that out. And the integral of dA is just the surface area of our Gaussian surface, so that is 4 pi r squared. And to find Q enclosed, we would need to take the volume integral of rho of r d tau. Here I will actually use r prime to not confuse it with the radius r that we defined earlier. So I'll add that here. So in this case, r prime goes from 0 to r, theta goes from 0 to pi, and phi goes from 0 to 2 pi. And d tau is r squared sine theta d phi d theta dr. So this is the integral we need to solve. So we'll start by integrating over phi. So next we integrate over theta. Cosine of 0 is 1, and negative cosine of pi is 1. I will now take all the constants out just to make this look a little bit better. And I realized I forgot to write dr in the previous line. Now we want to solve this integral. So I'll be using integration by parts. I'll define u as r prime squared and dv as e to the negative 2r prime over a dr. These r should also have primes on them. Okay. And du is 2r prime dr prime, and v is negative a over 2 e to the negative 2 r prime over a. So if we do this and follow the integration by parts formula, now we use integration by parts again for this part of the equation. I will define u as 2r prime and du will be 2 dr prime. V will be negative a over 2 e to the power of negative 2r prime over a dr prime, and dv, or this is dv, and v will be a squared over 4 e to the power of negative 2r prime over a. Now we continue to solve this. I'll start with the integral. Now I will substitute in numbers for r prime. And I will also carry out this minus sign. So e to the power of 0 equals 1, and I will actually continue this on the next page. So now we can solve for the electric field. And we get this. So with this electric field, there is a slight displacement between the nucleus of the atom and the electron cloud, which is represented by the r term that I mentioned earlier. But the shift is very small, so we can expand the e to the power of negative 2r over a term, assuming that r is much less than a. So we use this expansion, e to the x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. So we can substitute this into the equation for the electric field. These higher order terms at the end here are very small, and negligible in our case. So using this much is a pretty good approximation. And now we multiply these together. And we have some terms that cancel out. Now these terms at the end are very small numbers, so negligible for our case. So this is what we get for our electric field. And a reminder from earlier, the equation for dipole moments is P equals QD, where D is the separation between the nucleus and the electron cloud, and in our case, D equals R. And we can make that substitution. So the equation for polarizability is dipole moments equals the atomic polarizability times the electric field, so we can solve for the dipole moment. So this right here is atomic polarizability. And that is the answer to our problem.